Alright, so now that we've talked about how to take the derivative of a function, we're going to talk about what it means for a function to be differentiable. And make sure you're taking your notes on the back of the handout I gave you at the end of class. So we'll start small and talk about what it means to be differentiable at a point. So to be differentiable at a point C means that the derivative of f at C exists. And so we'll notate that as f prime of C. And this is one of those explanations that probably seems like duh if it's differentiable at that point, then the derivative exists. But we still need to kind of start small and then we'll work our way to the less obvious things about differentiability. So that's what it means to be differentiable at a single point. So the next step is on an interval. So to be differentiable on the interval AB, and that is not inclusive, means that the function is differentiable at every point on that interval. So again, this may still seem a little bit obvious, but basically we're saying that if you're saying a function is differentiable on a whole interval, that means we can take the derivative of any of those values between a and b. Okay, so now that we've learned how to take the derivative, you're going to learn how to use that to prove differentiability at given points. So next we're going to write like our formal definition for differentiability at a point. So keep in mind that the basic original definition of the derivative involves limits. And so the definition for differentiability will also involve limits. So a function f of x is differentiable at the point x equals c if and only if the following is true. If the limit as x approaches c from the left of the derivative function equals a certain value, and that value is the same as the limit the limit of x approaches c from the right of the derivative is the same value. And we're going to add in where L, that value for my limit I'm getting here, is a finite value. Okay, so this looks complicated, but really it's like going another layer past thinking of continuity. So continuity is saying that the limit just of the function itself, so that's dealing with y values, approaches the same thing. This is saying that the slope, right, the derivative is just the slope, the instantaneous rate of change of the function. So it's basically, you can just think of that whole thing as f prime of x. Okay, and that's the alternative definition of the limit, if that didn't look familiar. Okay, so you're basically finding, oh, I guess I should fix that part. This guy right here. There we go. Okay. So basically we're just trying to show that the slope of the function from the left of a value and the slope of the function from the right of a value are the same slope. Okay? So let's kind of put that in layman's terms below here. So in other words, the derivative, which again, thinking slope when you see that, slope of the tangent line, from the left of an x value must equal the derivative from the right of that same value. So let's look at some cases where this is not going to be the case. Okay, so on your note sheet you have these examples already written out for you. We're just going to kind of go through them together and make sure we're really understanding why they're examples of non-differentiable functions, or at least at a point. So this first one occurs whenever you have a function that has a corner. The most popular example is the absolute value of x, and it's differentiable everywhere but where x equals 0. So that's the problem. And if we come over here and look at x equals 0, you can see that the graph is continuous, okay? So we're not talking about if there's a discontinuity here. We're thinking about the slope. And as you can see, the slope from the left of 0 is negative, whereas the slope from the right of 0 is a positive slope, okay? And this is a little confusing because even though I'm coming from the right-hand direction and it looks like I'm going in a downward motion, just remember that if you're going up to the right, that's a positive slope, okay? Regardless of your personal direction you're looking at it from. Okay, ooh, that's pretty. So because this is a positive slope and a negative slope, okay, is going down to the right, whether we know the value of it or not is really not relevant, although we do because it's just absolute value of x. But the fact that one is positive and one's negative means that they can't be the same. So in fact, this slope is a -1, and on the right the slope is a +1. So we would say that the slope from the left does not equal the slope from the right. So that's why that function is not differentiable at the value x equals 0. Now, as a reminder, if this were a free response question and you're trying to say that, you would have to write it in the limit notation. So the limit as x approaches c from the left of f prime of x does not equal the limit as x approaches c from the right of the derivative function. Okay, so both of those mean the same thing. One is kind of just like the thinking way of looking at it, and the other way is the more formal notation. Okay, so the next reason a function may fail to be differentiable is because of what's called a cusp. Now, some people argue, like, what's the big deal between a corner and a cusp? Technically, a cusp means that it's kind of like curving to meet at a point versus like a linear function meeting at a point. And because of that, the slope is actually getting like infinitely steep. Not exactly an asymptote per se, but like if we kept zooming in on this forever and ever, it would just keep on getting steeper and steeper and steeper. So that's, in my opinion, why they're called two different things. But so yes, at 0 we have a problem. And that's because the limit as we approach 0 from the left is getting more and more negative. And again, if we zoomed in, it would just continue so. Okay, and then, of course, if we looked at the limit as x approaches 0 from the right, it would be the opposite issue. So again, even though from the right I'm going in a downward motion, that's an up to the right type of graphical motion, which means it's getting more and more positive as I come from the right. So again, we would not be getting any sort of matching slope coming from the left and right directions. Okay, another way to think about these that we haven't really talked about too much with both of these is, you know, if you're drawing tangent lines to curves, you want it to touch at one point. Well, with a corner, we don't know what that actual tangent line might look like, right? So it could look like this one. It could also maybe look like that one. Maybe it was flat. We don't know. But that's the thing when we're at a corner, or the same thing is true for a cusp. We don't know how that tangent line would lay because it's some sort of point, like pointy point, not like point xy, that we just don't really have a way to visualize what that tangent would even look like there. So moving on to the third type, a vertical tangent line. So for this function, you know, you could pick a point here and draw the tangent, or you could pick a point over here and draw the tangent line. Ooh, that's not very good, but you get the idea. The problem occurs kind of in the middle, right? Right at 0, again, that seems to be a common issue point for certain functions. To draw a tangent to that would actually mean to draw a vertical slope. And when this happens, we have to think, how would you write the derivative if the slope was for a vertical line? So if you want to think about, you know, we're thinking of rise over run with slope. Vertical lines have a lot of rise, but they actually have 0 run, okay? And when that occurs, it gives us an undefined slope, okay? But in this case, remember, we're now thinking of slope as derivatives, so it simply means that we don't have a derivative at that point that we can calculate. So anytime you have a vertical tangent line, those are lines that have undefined slope, so we can't differentiate there. Okay, so for these first 3 examples, these are examples of graphs that are continuous, but still not differentiable on the whole function. Okay, so maybe jot that down on your paper. It might be easier to kind of write yours over here on the side. But somehow notate that these are 3 separate examples of functions that, I can trace all the way across and there's no issue with continuity. However, that has not guaranteed us that it's differentiable at all these points, because for each of these, there happens to be a point of discontinuity at x equals 0. Okay, so moving on to the 4th one, this is our first example of a function where it's not the slope that's the problem. Okay, so the slope from the left of 0 and the slope from the right of 0 are actually the same slope. So in this case, we know that the slope from the left, this is a horizontal line, so that slope is 0, and that the slope from the right is also a horizontal line with the slope of 0. So it's not the slopes that are the issue. The issue is that there is not continuity at x equals 0. And if there's not continuity, I can't find the slope of 0. So whenever there is any type of discontinuity, we can't find the slope at those points. So it seems like we were getting closer to what we were looking for, but because the value at 0 itself is not continuous, we can't go any further. And then there's our final function. So you may have remembered this from a very long time ago at the beginning of Unit 1 when we talked about things that cause a limit to not exist. Okay, so again, oscillating functions. This is one where the limit, that's right, limit does not exist because of that. Simply because as I come from the left and the right, we don't know what value it's approaching. So if we don't know what's going on with the y values here, we definitely don't know what's going on with the slope. So because of the limit not existing, this means that it's not continuous. It's just another way that that might occur that's a little bit less obvious than the prior example. So if the limit doesn't exist, that means it's not continuous, which means we're not going to be able to find the slope at that point. So these last 2 examples are kind of functions that aren't even continuous to begin with, so they're not differentiable for that reason. So this brings us to a differentiability theorem that states, if a function f of x is considered differentiable at a given x value c, then that implies that it is continuous. So again, just kind of going back to the basic idea that a derivative gives us the slope, the instantaneous rate of change at a point. So if we can do that, that means there has to be a point there, and if there's a point there, then we're able to say it's going to be continuous for that part of the function. Now, the contrapositive of this is also true. So I don't know how many of you have taken logic or have much experience with this, but contrapositive means the opposite, so kind of the inverse, the not statement, and the reverse order. So wrap your head around that for a second. In other words, if we took the second part of what we just said, f of x is continuous at x equals c, and we put the inverse of that, which is that it's not. So let's say if f of x is not continuous at a point, okay, then the inverse of the original antecedent is now false. So if it's not continuous, well, we don't need a comma there. If it's not continuous, then it's also not differentiable. Okay, so this is kind of confusing to remember. So here's kind of my, it's not really a metaphor, but just kind of how I remember it. So hopefully we all can kind of understand the difference between, or not the difference, but the relationship between squares and rectangles, right? So let's think about that. Okay, so bear with me. We're, being understanding that I'm not drawing a perfect square. But let's say this is my square, and my square is going to be differentiability. I definitely can't fit this in here. Oh gosh, differentiability. Okay, so differentiability implies that it is continuous, but it does not go in the opposite direction. Okay, so differentiability implies continuity. So that's a one-way street. Similarly to how we say, like, a square is technically follows the definition of a rectangle, but just because something's a rectangle doesn't guarantee that it's a square. So if we know a function's differentiable, that implies it's also continuous. But just knowing a function is continuous does not guarantee that it's differentiable at all the x values. And our first three examples kind of showed this particular situation. So going forward, you will need to be very comfortable with the theorem itself, that differentiability implies continuity, and also the contrapositive. It's super helpful sometimes. They'll give you like this really complicated function to find the derivative of, but if it's not continuous at a given point, you don't need to go through all that work to find the derivative at that point, because it's not going to exist. But there will definitely be plenty of questions that make sure you really understand this relationship between differentiability and continuity.